Okay, so good afternoon, everyone. Today we're going to continue our discussion on this theoretical part about our statistics. So here our discussion is concentrated about the estimator. We call an estimator theta hat, which estimates a parameter theta. So in all this class, we specify a distribution by parameters, right? So for example, for the normal distribution, we specify it by mu and sigma square. For Poisson distribution, we specify it by lambda. For exponential distribution, we specify by lambda and etc. So these are the parameters that specify the distribution of a random variable. And all the discussion is about that we have an IID random sample of size n denoted by x1 to xn from that distribution. And from this xn, we construct an estimator called theta hat. So theta hat is a function of x1 to xn. So I can put it here. So I'll just say this t is a function. So for example, the simplest case is that theta hat is just what we defined as xn bar, right? So that's a function that adds up x1 to xn and divide the sum by n. So with this, then we want to talk about how good the estimator is. So in terms of estimating theta. So regarding the performance or properties, we talk about the bias, which is the expectation of theta hat minus theta. So we talk about expectation because in our discussion, x1 to xm are random variables. So therefore, as a function of them, theta hat is a random variable. So the average behavior of theta hat is its expectation. So we want the expectation to be exactly theta. That's called unbiased. The variance is defined by definition in this way. So you can see that in the variance definition, we are doing theta hat minus its expectation, not theta, because its expectation may not be theta if theta hat is biased. So this variance is another property of the theta hat, which measures how variant this theta hat is around its own expectation. So if the variance is big, then if we draw different samples x1 to xn, the corresponding theta hat values could vary a lot. That reflects the variance. And finally, this is the most important property, the MSE, which is defined as the expectation of the square difference between theta hat and theta. So here we're using theta, the parameter of our interest, instead of the expectation of theta hat. So we can actually decompose this into the bias square plus the variance. Okay, so to show that I actually can leave this to you to do this exercise, it's basically algebra. So to go from here, what you need to do is to write the square as theta hat minus its expectation plus its expectation. So when we do this, right, we are basically doing nothing. Minus plus cancel each other, minus theta square. So if you start from here, you open this square up as a square of theta hat minus e of theta square and a square of e of theta hat minus theta. So, and then you are going to show that the cross term is equal to 0 with the expectation. So with that, then you can show the two terms you get are basically bias square and the variance. So you can show that yourself. So I will leave that to you. But if this is something that you couldn't figure out, please feel free to come to the office hour or just raise this question in the later lecture. So we will try to do this. Okay, so we talked about the three properties, and then we introduce a very important result, Cramér-Rao inequality, which gives us the minimum variance of an unbiased estimator. So this estimator is restricted to be unbiased, and still it's a function of this random sample, x1 to xn. Okay, and so here we denote this by G. Okay, this is a function that maps x1 to xn to the estimator. So this result says that the minimum variance of this unbiased estimator theta hat is 1 over m times the Fisher information of parameter theta. So what is the Fisher information? We defined it here. So it's defined based on the log density function and one random variable x from the distribution f. Okay, so this random variable x follows the distribution that has density function small f. So in this Fisher information definition, so you can see that we write this as the log likelihood, but the likelihood is a function of theta. And the likelihood definition involves this one random variable x. So last time we said, okay, when we talk about expectation in the definition of this Fisher information, expectation is with respect to random variable. And theta in our whole class is not a random variable because we're talking about, we teach you the statistics under what we call the frequentist framework paradigm, where the parameters are regarded as fixed and only the random variables from a distribution are random. So later you may learn about Bayesian statistics, and that's a different story. But here in our context, the parameter theta is regarded as fixed instead of random. So therefore, the expectation is with respect to the random variable x, which is involved in this log density function, or you can say it's the log likelihood function of theta with one random variable, just one x. Okay, so then we just write this log likelihood as log f density at this random variable x. It's big X because it's random and parameter theta. So it evaluates how much information does the density provide about the theta. So we can think about it. This Fisher information is some property of the distribution alone. It's not depending on our actual observations or realizations of X or actual data. The reason is that we are taking this expectation. So whenever you take expectation, you are talking about the distribution, the nature, the population, instead of just your data, your random sample. I hope that makes sense. So therefore, if you specify a distribution like a normal distribution or Poisson distribution, then the Fisher information for the distribution's parameters is given. And this Fisher information may depend on theta. So it may vary as theta varies, or it may not. So both could happen. It's just a property of that distribution. So later we're going to do an example for the normal distribution and try to derive the Fisher information for the parameter mu, the mean parameter. Okay, then we said that an alternative definition of Fisher information is that you take this log likelihood with one random variable just to do the differentiation for 2 times. Okay, so this is the second derivative of this log likelihood with respect to theta. And still, it involves that random variable x. And then we take the expectation and do a negativity. So this will give us the alternative definition of Fisher information. And we can show you that these two things, these two definitions are equal to each other. But I have to say that this is not general for any function of theta. It's just for the log likelihood theta defined in this way. And this is because of a special property of our density function. That is, it integrates to 1. So last time we stopped in the middle of this proof, and we're going to complete it today. So we start from this density property that now that density function, its argument is any value of the random variable. So it's not theta, but x. So when we do the integration with respect to x, it's 1. That's the definition of the density. So now we do differentiation on both sides because it's 1, right? So 1 doing differentiation against theta is 0. And we have this as 0. And so the Cramer-Rao inequality, the one we try to show here, requires smoothness conditions of the density. That's essential. So all the discussion we gave you right now are assuming this f to be smooth. And smooth can be roughly think as something you can easily exchange integration and differentiation, which we will do. So allowing that change of order between the differentiation against theta and the integration, we move this inside, and then you see what happens. We will have this as equal to, let me see, I think there is a mistake here. It should be 0 instead of 1. I wrote it wrong. Okay, so because this follows from that. So this is 0. And also, we can see that in this Fisher information, we work with log density, log f. So if we take and we will do differentiation, right, against theta for the log f. So now let's look at this differentiation of log f. So then we use the chain rule, then we are going to get the derivative in this way. So 1 over fx theta is from this log part, and then we do differentiation on f. Okay, so using this is a key relationship here based on the chain rule and the log property. We would write this differentiation of f, so derivative of f, just as the derivative of log f times f. Okay, so using this, and from 1, we know that if we do the integration on the left-hand side, it's 0, right? So we have 0 equals to the integration of the left-hand side for x, which is equal to the right-hand side integration for x. And now we have the definition of expectation. So a function of x times density x dx, doing integration, we are getting the expectation, right? That's the definition of expectation. And here we change small x to big X because big X is the random variable. Small x is just a value that big X may take. Okay, so do we see this connection from here to the expectation? That's the definition. Okay, so I think for today we just have 2 of you showing up. I hope more of you can show up, and because that way I can see your response and also whether you have any confusions. Okay, thank you. So now we have this result already. So if we do just one differentiation, then log fx theta expectation is equal to 0, and we'll continue from here. So now let's look at this thing. Okay, let me give this a number so we can make our discussion more easily. Okay, let me call this number 2. So this equation is from number 2. So now let's do differentiation again for number 2. So let's do differentiation against theta one more. So do d theta on both sides of 2. Okay, so if we do that, then let's see what we get. This is the left-hand side. For the right-hand side, we are going to do this on a product, right? And also, so we know the rule is that we do differentiation on term 1, keep term 2 unchanged, plus differentiation on term 2, keeping term 1 unchanged. So we're going to do that. So then for term 1, if we do its differentiation again, so it will be d squared d theta squared log f. Okay, this is the first term. And the second term is that we keep this unchanged. Okay, times d theta. Right, so this is it. We're just applying that calculus rule. Okay, so what else? Now, let's see. For the left-hand side, we have the second derivative, which is what we need in the, actually not yet. So for the left-hand side, it's actually the, from the, sorry, in the alternative definition, we are going to do the log thing. So not yet here. So the log thing is right here. Okay. So what I want to say is that now if we do the integration of x on both sides, what would happen? So if we do this on dx, okay, integration dx on both sides, let's see what we have. So the left-hand side is okay. And this actually we know is still 0 because we still have that smoothness condition to help us. So basically we can do this. If we move it out. Sorry, beta dx, right? This is still 0 because this is equal to 1. So the smoothness condition allows us to swap differentiation, and integration is the key. So the left-hand side integration is 0. For the right-hand side, let's take a look. So I'll say left-hand side, sure, that's LHS, left-hand side. The right-hand side, we can see if we do the integration here, dx, then by definition, let me just write one more step. Okay, times fx theta. Okay, by the definition of expectation, this is equal to expectation of d theta squared log f. I'll change the small x to big X to mean the random variable. This is it. Okay, by definition. And now go to the second term. Second term right here. So we are going to use our 2 again. Okay, so this d theta fx theta can be expressed by this equality. Okay, so let me just use that. So I'll put the first term here, d theta log fx theta. Okay, second term, I'll use 2 to use the right-hand side. d theta log fx theta, right? Times fx theta dx. Okay, so this whole thing from here is by number 2, by the result of number 2. So I do the replacement. So then for the second term, what it is, you can see that it's basically, I just go one more step. It's d theta log fx theta squared, okay, times fx theta dx. Then again, by the definition of expectation, this is equal to expectation of d theta log f capital X, random variable X, theta squared. Okay, so did you see that? This is already our definition of Fisher information. So now because the left-hand side equals the right-hand side, so we have this term plus this term equals to 0. So therefore, we have expectation of d theta log fx, random variable x, theta square equals to negative expectation of d squared d theta squared second derivative log f big X theta, right? And then both is defined as our Fisher information. So we proved it. So here the proof is basically using that smoothness condition to change integration and differentiation against theta. And the second equality is also crucial. So we can actually relate the derivative of f against theta to the derivative of log f against theta. So this is also a special thing we used. So together we get this equality. So these two are the two ways to define Fisher information. Okay. And okay, that concludes the Fisher information definition. So now let me give you one example about the computational Fisher information before we go to the Cramer-Rao lower bound proof. Okay, so the distribution of the midterm was covered in the discussion sections. So if you missed the discussion sections, you can watch the recordings. Yeah, they were posted. And yeah, so if you have any questions, you can come to the next office hour or schedule an appointment with me. But I want to emphasize that, so the raw score is not that important, but your relative ranking in the class is important. So basically, I wouldn't say that we will curve the grades so that we will have this percent of A, this percent of B. That's not that strict. The percentages will not be very strict. What we will essentially do is to account for both the raw scores, the overall scores after you have the final, and your ranking for the overall score. So we'll make sure that for the breaks, right? So for students who have similar raw grades, raw scores, they would receive the same letter grade. So basically, we're going to look for gaps based on the relative ranking and also the raw score. That's how it works. So that's why from year to year, the percent of people getting A or B may change slightly. Okay, so, and also for the final, I think I'm going to make a formal announcement in the CCLE later. So we are going to do in-person final. I think that will be better for everybody. So we are going to use the slot assigned by the university. I think it's in the very big room, the Haynes 38 or 39. I think it's a very big auditorium. We're going there, and so we're going to do the in-person final. So you have more time and you can write down your solutions. So yeah, and also this time we had, for midterm, we had a lot of technical issues that we'll try to avoid that in the final. Okay. All right, so yeah, so let's do one example about Fisher information. Okay, so let's see that we have our x1 to xn from a normal distribution with mean mu variance sigma square. So here we just want to find the Fisher information of mu only. Okay, to be strict, actually in this case, since we have two parameters, so like if I'm going to a graduate level class, I should tell you that the Fisher information should be for the two parameters jointly, and it will be a 2x2 matrix. So the Fisher information for two parameters should be a matrix. But here we simplify it. We just say we look at one parameter only, that's mu. So here the Fisher information we talk about is just a scalar. Okay. So how do we calculate it? Let's go to the density. Okay, so the answer is that. Let's look at the density function, PDF. Okay, and we are only concerning about mu only. So let's pretend that sigma is known. Okay, so assume sigma square is known for now. Okay, so this density function we can write it as this. This is what I emphasized. I said that if you want to know one density function, then it should be Gaussian, normal distribution, because it's the most commonly used distribution out of all the distributions. Okay, so this is x minus mu squared, and it has that bell shape. So this is the density. Now, for the Fisher information calculation, we need a log density, right? So the log will be what? It will be, let me just write it, negative log root 2 pi sigma minus okay, that's the log density. And now we are going to take differentiation against mu. Okay, so d mu. Okay, it's what? The first term doesn't involve mu, so it's gone. We are only left with the second term. So denominator stays, and it's 2 times x minus mu, and there's a negative sign, minus 1, right? That's the derivative. So then 2 and 2 gets canceled, and minus minus canceled. So we are left with x minus mu sigma squared. Okay, so now I can use either definition to calculate the Fisher information. But up to this point, I can see that the second definition is easier, because if I go to one more differentiation against mu, I know mu can be gone. So then I'm left with a constant, and that expectation is just straightforward. So let's use the alternative definition. So d squared, d mu squared. Okay, one more round of differentiation. It's obvious, just negative 1 over sigma squared. So you see, it has nothing to do with x. Okay, not involving x anymore. So therefore, the Fisher information here defined as the negative expectation. Capital X mu. Okay, this would be just the constant, right? So putting the constant here, minus, then it's just 1 over sigma squared. So you see, in this case, it shows that the Fisher information in the normal distribution about the mean parameter mu has nothing to do with mu itself, but depending on the variance. So you can see the intuition of Fisher information would make sense here. The smaller the variance, the larger the information. What does that mean? It means that your random variable x, one random variable x, will tell you more information about the mean parameter, right? Since given a smaller variance, your density is more concentrated around the mean, then you have more information about the mean, right? So that will give you the intuition. So the intuition is that the information the density contains about mu is inversely correlated with the variance. Okay, so now let's come back to the Cramer-Rao lower bound. Okay, so we can see that this is the Fisher, so all the Fisher information we've defined so far. So our definition of this Fisher information is based on one random variable x from a distribution f, okay, specified by theta. So this is the density function, and I just leave out the argument. To me, it can be any notation, but that's the function, density function f, given the theta. So now let's see that if we have n random variables, okay, how about x1 to xn? They are IID from the same density function specified by theta. What if I use them jointly to find the information about theta? Can I get more information? So then here we can define this called joint Fisher information. And the joint Fisher information in some textbook, it's written as IN. Put a number of random variables or a random sample size in the subscript. The IN theta is defined in the same way, expectation of the log density, but expectation of the squared first derivative of log density. But here the density is the joint density. So in other words, it's actually d theta log of all the random variables x1 to xn, joint density. Okay, this is the definition of this joint Fisher information. So now you can see clearly this expectation is with respect to all the random variables. Okay, x1 to xn. And now, given that they are IID, right? So given that they are IID, we can go one more step. So we know that fx1 to xn, so make a side note. Because of IID, theta, because of IID, they are factorized. They can be factorized as just the f of each xi given theta, right? Now we put this log at product. We would have it as sum of log, right? We know log product is equal to sum of log. So therefore, this is actually equal to, okay, d theta of log of, d theta of sum I from 1 to n log, okay, f xi theta, right? It's this thing square. Okay, does that make sense? Okay, so, and furthermore, what else do we have? So given this Fisher this joint Fisher information, then you can see that we actually, I can skip it. Maybe I want to skip a few steps here because otherwise I need to show, like we need to expand this, this is like the sum, right? So this is a square, and we will need to do something similar to what we prove right here, to like the proof for that these two definitions are equal to each other. So we will do something similar to show that they are the same. But let me just go to the alternative definition again. So like alternative definition, and that can be more straightforward. So the alternative definition of I and theta is based on the second derivative. So the proof that these two definitions are the same are actually what are basically the same as what we did. So you can just follow that by changing x to x1 to xn. So things should follow. So in the alternative definition, I will go to the second derivative. D squared d theta squared log f x1 to xn. Okay, that's it. And because of this, right, so this can tell me that log f x1 to xn theta will be equal to sum of log fxi theta. Okay, and we're going to use that here. So this will tell me d squared d theta squared sum log fxi theta. Okay, and I know that the derivative can enter the sum because this is a finite sum, I from 1 to n. So I can put this inside the sum. And also the sum can be exchanged with expectation. So with that, then you can see this will give me minus sum I from 1 to n, expectation d square d theta square log fxi theta. Okay, right, that's it. And now we are going to use the fact that x1 to xn are IIDs. So therefore, regardless of the I, the expectation is always the same, right? And each xi is just a representative of this one random variable x. So because of IID, I'm having each expectation inside the sum to be the same thing. And each expectation here is just our definite, or minus, I should say. Minus this is just our expectation of, it's just the minus expectation is just our Fisher information. So this is, I will say, same for I, for all the I. So therefore, I can say that it's just the sum of the same item. So I can write it's n times the same item, and that's our Fisher information. So therefore, the special thing about Fisher information is that it scales with the number of random variables. So your sample size gets into the joint Fisher information. The larger the n, the larger the joint information. So in other words, you can see the power of sample size. Larger the sample size, more random variables you observe from this F, then more information, more Fisher information you have about this theta. Okay, does that make sense? Okay, so then with this, coming back to the Cramer-Rao lower bound. So we call that the Cramer-Rao lower bound. Okay, this is saying what? So why did we go product from I to, from 1 to m for? So you're talking about here, right? So this is the product on the normal scale. This is on the log scale. So when we go from log, so if we have log of a product, it becomes a sum of log. Yeah. Okay, so now let's come back to the Cramer-Rao lower bound. So what we're saying here is that we let theta, okay, to be, I'll stick with G, to be x1 to xn, and it is an unbiased estimator. Okay, and as in our regular setting, x1 to xn are IID from a density function specified by theta. Okay, so that's the setting of the Cramer-Rao lower bound. And then the result is that, so the result is we tell you the minimum variance of this unbiased estimator is greater or equal than 1 over n times the Fisher information. And based on my discussion just now, this is actually the joint Fisher information with sample size n. Okay, so that's the conclusion. And how can we prove it? I think the proof is actually very important, actually very interesting, I should say. The proof will use a very important property I hope everybody is known or should know after this. So let's say that we have, so let's define this, well, sure, I should say theta is a random variable. Okay, so I would say a general fact. Maybe we should say the general fact first is that for two random variables, x and y, okay, both scalar, we have this important result, that is the covariance of x and y is less or equal than the variance of x times the variance of y. Okay, and this is actually a result from a famous Cauchy-Schwarz inequality. Okay, I don't know how many of you have heard of this Cauchy-Schwarz inequality, but I would say that if the high school math education is very rigorous, it should have covered this in high school. But if not, I think this is something we should know. It's a very important thing. So it's basically, so the general form, okay, the general form of Cauchy-Schwarz is this. So if you have two sequences, AI and BI, then the sum of AI and BI is less or equal than, okay, I should say this, the square of sum of AI BI is less or equal than the sum of AI times the sum of BI. Sum of AI square, sum of BI square. Yeah, so this is the general form. Okay, and you can also see that the special case of this is actually everybody uses is this x, y, right, is less or equal than, no, I should drop it. That's a different thing. So my bad. Yeah, but this is the Cauchy-Schwarz. And so coming back to the covariance and the variance relationship, this can be seen by the definition. The covariance is defined as just x minus expectation of x times y minus expectation of y. Okay, that's it. And on the right-hand side, we have the, okay, I think I missed one thing, sorry. It should be square, my bad. It should be the square of the covariance. Yeah, that makes sense. So then it should be this square. That's the left-hand side. And then variance of x, we know it's defined expectation of, okay. So in other words, you can see in the traditional Cauchy-Schwarz inequality, we are basically replacing the sum by expectation, okay, in each term. So it's just that whether you do the product first or you do the product first or you do the sum first. Okay, so, and a way to see why this makes sense, I can just go one more step to help you know why this makes sense, or it's easier to know this result, is that recall what we define as our correlation. The correlation, Pearson correlation of x and y is actually defined as covariance of x and y divided by the square root of variance of x times the square root of variance of y. So I'm not sure if you learned this from your probability class, but I'm just trying to just talk about this as a result. So in this Pearson correlation definition, we know that the correlation has the range of -1 to +1, right? Pearson correlation. -1 means negatively perfectly correlated. +1 means positively perfectly correlated. And then you can see what we have here. This one, it can be obtained by square the Pearson correlation. If you do the square, you would have the covariance square of x and y divided by the variance of x divided by the variance of y. So clearly, this would be between just 0 and 1, right? Because the -1 becomes 1 after you do the square. So therefore, this can also tell you, since this is less or equal than 1, we actually can go back to this result from the Cauchy-Schwarz. But I should say that Cauchy-Schwarz is the reason of this inequality. Because of this inequality, when we go to the Pearson correlation square, we can have the square under 1. But I will just say that if you know the definition of the Pearson correlation, it's easier to remember this result, the direction. Okay, so we're going to use this general fact, right? Since here we also have its variance greater or equal than something. And this inequality is the thing we're going to start with. So basically what we will do, the idea for this proof, okay? So with this general fact, the idea of this proof is to use some random variable t, okay? I'll call it t, and show that, and the fact that the variance of our estimator, theta hat, based on this fact, is greater or equal than the covariance, squared covariance between theta hat and this random variable t, divided by the variance of this random variable t. Okay, this is our idea. And we're going to show that for some t, this lower bound is equal to 1 over n times Fisher information. That's the idea. So the key is to find that t construction so that this general result gives us the Cramer-Rao lower bound. And you can see that this construction of the t is I would say, it's very interesting, right? It's where the magic lies in. So to really do this, we are going to tell you that based on what we have, then the t construction, if the t is actually based on the knowledge we just gave you, it's about the derivative of the log density. Okay, so here, let's see if we define this t to be just d theta, and thus a t is also a function of our random sample x1 to xm, just as our unbiased estimator is. So if we define this t to be just the log joint density of x1 to xm given theta, okay, this is a random variable because x1 to xn are evolved. And we're going to use some results we already derived about the special thing about this log density and the special thing about its derivatives that will all get into play. So you can see that based on what we just wrote, right, in the question we just answered about the previous page, the log density, joint density is equal to the sum of log marginal density, right? So we know this is equal to d theta right? So this is what we wrote in the last page. Okay, and let's move this differentiation inside. Okay, that's it. Okay, and one more step, chain rule, right? To simplify this differentiation of a log density, which is just fxi theta, the chain rule we did, d theta f, right? d theta f xi theta. Okay, this is the random variable t we constructed. And we already know that for the variance of t, which is what we need for the lower bound, for the variance of t is what? Is equal to the expectation of t squared minus the square of the expectation, right? We have used this result again and again. And the expectation of its square, recall that that is our definition of the joint Fisher information, right? Because this is the derivative of log joint density, which is what I wrote here, right? This is the definition of the joint log, the joint Fisher information. So therefore, the first term is just in theta, joint Fisher information. Second term, expectation of t, this, we can show that it's equal to 0, which is based on the same argument as we have. So the ET, okay, just let me give you one more step. It's just equal to, right? This is the t. It should be d theta log f. Okay. So it should be, I should write small x1 to small xn. This thing times the density. Okay. Joint density dx1 to dxn times 2 dxn, right? This is the definition of the joint expectation. And now I am going to put the D formula inside. Okay, so this is the T. I put that inside, and then I can show that because this joint density can be factorized as fx1 theta times 2 fxn theta, I will have a lot of cancellation here. So finally, this is equal to 0. Okay, so I will just put this here and let you verify it. So I from 1 to n, d theta f xi theta f xi theta. Okay, and then this joint density can be written as fx1 theta times 2 fxn theta dx1 dxm. Sorry, I should say this is a joint integration. So the integration is for x1 to xn. So we have n integration here. So you can do the cancellation and then use the exchange of differentiation and the fact that density integrates to 1. So the same thing we used before. It's just that you need to work with n x1 to xn here instead of just 1x. So I'll state that and just say, okay, we can show this is equal to 0. So expectation of t is equal to 0. There's no problem of that. Or maybe an easier way to see this, right? This is a little bit complicated. Or you can show, I give you a simpler solution. Expectation of t based on this, right? It's just I exchange the sum and expectation. I from 1 to n, expectation of this d theta f xi. Right, this is simpler. Then we use the fact it's IID. So the sum becomes just n times expectation of 1 xi. Let's say x1. x1 d theta. Okay. And this is equal to 0 is what we already showed in that proof for the equivalence of the two definitions for Fisher information. So this holds. Okay, this is the simple way to put it. So now you see, given the expectation of t is 0, the variance t is just equal to the expectation of t squared. It's the joint Fisher information. And the joint Fisher information is just 1n times I theta. So seeing here, we already give you the variance of t is equal to n times I theta. So what's left for us is to show that the covariance of theta hat and this t is equal to 1. With that, then the proof is done for the Cramer-Rao. Okay, so we have variance of theta hat greater or equal than covariance square of theta hat and t divided by the variance of t, which is n times I theta. We have this already. And we are left to show the covariance of theta hat and t equals to 1. That's the last step. Okay. And to answer this question, to find this, we are going to look at the covariance definition. And similar to the variance, that can be written as the expectation of the second moment, or the second moment minus the square of the first moment. The covariance can also be written as just the expectation of the product minus the product of expectation. Okay, so if this is something that's not familiar to you, you could try prove it. It's still just one line, just using the covariance definition. The covariance is defined as theta hat minus its expectation times t minus its expectation. Okay, you just open it up, try to expand it, and then you can see with some cancellation, you can get here. Similar to how we prove this relationship. Okay, and now for this expansion, you can see, because we already showed expectation of t is 0, so the second term is gone. So the covariance is just equal to the expectation of theta hat and t. Okay, so now let's do it. So for this thing, we are going to use the definition of expectation. And recall that our theta is this g function of x1 to xn. So we're going to use it. All right, so basically this expectation, let me just write one more step. The expectation, by definition, okay, it involves random variables x1 to xn. So it will be this joint integration of x1 to xn. For theta, it's the g function. And since we're doing integration, I'm using lowercase for all possible values of random variables x1 to xn. And this is theta. And the t, we already have here. Okay, so I just put this t here. Summation d theta fxi theta fxi theta. Okay, this is my t. And then I need a joint density, the joint density for x1 to xn. And I'm going to use the IID result directly. Okay, so I from 1 to m, fxi theta. This product is the joint density. Finally, dx1 times dxn. That's the joint integration for expectation of theta hat times t. Okay, so how can we simplify stuff? One thing we can see here is what's interesting about this term. So what's interesting about this term is that if you think about the chain rule, so let's see, inside the summation, right? So we can multiply this product into the summation for each term in the summation. Then you can see, let's say for I equals 1, then this fx1 theta will cancel the fx1 theta right here. Okay, so let's look at this term. So for I equals 1. So then look inside the sum, d theta fx1 theta divided by fx1 theta, this is inside the sum, times the product. So we can see in the product, we have fx1 theta. That can be canceled with this. So then we have what? We have d theta fx1 x1 theta from the numerator, okay, times the product with the first term removed, I from 2 to m, fxi theta, right? This is what we have. And what is this? This means that you are just taking the differentiation for theta in the first term, fx1 theta, keeping the remaining terms unchanged. So if you see this result, then you can see that basically this whole thing, so you can see, let me put a sum outside, I from 1 to n. Okay, let me put the sum outside. d theta fxi theta. Okay, this is the term. And now let me put this term inside times, maybe this better to do this, times this product. Okay, I'll just use a different index to avoid confusion. J from 1 to n, fxj theta. So I move the product inside the summation. Then you can see that each time the denominator is going to cancel one term in the product, but the cancel term will stay in the numerator in its derivative form. So therefore, you can see that this is exactly applying that calculus differentiation rule to a product of things, right? So we recall that if we have a product, we want to take differentiation, then basically we take differentiation for one thing at a time. So this is just equal to d theta of this product, j from 1 to n, fxj theta. So this is the key part. You see, when I'm taking differentiation for this product, I will do differentiation for each term, keeping the remaining term unchanged. And that's exactly what I have on the left-hand side. Okay, so seeing this connection, right? And so I can change j back to I. It doesn't matter. It's just an index, d theta, I from 1 to n, fxi theta. So with this, then let's go back to the expectation of theta hat times t. Going back, then you can see the integration g x1 to xn, that's my definition of the estimator theta hat, stays. And the second, third term becomes just d theta, the product joint density of x1 to xi theta. Okay, dx1 dxn. And finally, again, I'm going to move this differentiation out of the expectation using the smoothness of the density. So moving it out, d theta, the integration stays gx1 to xn, my estimator. And here the product of this fx1 to fxn is just the joint density. I can restore it to be the joint density like this. Okay, by IID, dx1, dxn. And finally, by definition, this is the expectation. This is the expectation. The integration is just the expectation of theta hat, right? Because theta hat is defined as g of x1 to xn. So I'm taking using the definition for expectation, and expectation is for the joint distribution of x1 to xn. Okay, finally, unbiased. Because we know theta hat is unbiased, this is the condition of my Cramér-Rao inequality. So therefore, it's equal to theta. So it's basically d theta theta. That's the expectation. And that gives me 1. Okay, so finally, you see, we go back to the covariance. We basically show the covariance is equal to 1. And then with this covariance equal to 1, using this general result, numerator becomes 1. We're done. So the variance of theta hat is greater or equal than 1 over n times Fisher information. So you have this lower bound based on that Cauchy-Schwarz inequality, as well as the fact that we can find this interesting construction of T. So that using this T, put the T into this relationship, we find the lower bound of this theta. So theta hat. So you see the final part, to have the numerator equal to 1, used the unbiased property of theta hat. Okay, so this is the whole idea of the Cramer-Rao inequality lower bound. And I still hope that people can follow this proof to see what the logic here is. And I would say the key message is that we are using the property of log density and its derivative and its integration. So those are special properties. It's based on the fact that f is a density function and it's smooth. So we can swap differentiation and integration. Okay, so you can see that those mathematical results were very interesting, right? In the old days, especially at that time, you can see that all these things were hypothetical. People are doing this calculation in mind without seeing any data. So that isn't that magical. So you can know the estimator's performance without even having actual data. And I would say in the pre-computer age, if you want to do data analysis, you want to have an estimator to summarize your data and talk about its properties, math is a requirement. And so that's why you can see in the old days, statistics was originated as a sub-discipline of mathematics. But gradually, as we have computers, we have more things to do, right? So now it's a separate discipline. So you can use computer as a tool to help you understand things, as I did in my last lecture, right? Use R programming to see how these things are actually. So basically, I want to say that math and computing are two important tools for doing data analysis. And this class focuses on math. Probably your other classes focuses more on computing. But I would like to say that we just all need to use our strength one way or the other, or both, to do data analysis. So that's what I hope that you can learn from this class. So even though you may not do mathematical statistics in the future, right, in your work, but these results are very interesting results to know, right? You know what's the best to expect from unbiased estimator. All right, so now let's go back to this example. This example we did before. Okay, this example, Fisher information for our mu parameter. So now let's use the Cramer-Rao lower bound to see how well our estimator performs. So recall that for estimating the mu, the estimator we have, no matter if you do MOM, method of moment, or if you do MLE, maximum likelihood estimation, the two approaches will give you the same estimator, X and bar, sample mean, right? Sample mean will be the estimator for mu. So now let's see how well its variance is doing. Okay, so now let's check back to the example, x1 to xm, ID from this normal distribution with mean, mu, variance, sigma square. So we know that if we want to estimate this mu, cut mu hat, so it doesn't matter if we do MOM or MLE, the estimator is just xm bar, average of x1 to xm. Okay, what's its variance? And we have seen this again and again. Okay, right? This should be something you can say immediately. What's the variance of xm bar? Given x1 to xn have variance sigma square. So it's sigma square over n, right? So that's the variance. Okay, and now you can see this is what? This is actually equal to 1 over n times 1 over sigma square. And that's the Fisher information we just computed for mu. right? We computed information of mu is 1 over sigma squared. So it means what? It means that this xn bar attains the Cramér-Rao lower bound. Achieves the CR lower bound. So in other words, this is the best estimator we can get. And furthermore, we should say that expectation is equal to mu, right? This is the first check we need. So it's unbiased. So it satisfies the Cramér-Rao lower bound requirement. It's an unbiased estimator. And besides unbiasedness, we verify that its variance is the smallest we could imagine, we could achieve. So therefore, we give this estimator a name. So we say this xn bar is a minimum variance unbiased estimator, short as MVUE, minimum variance unbiased estimator. So this is the best estimator you could imagine, you could achieve. So you can see mathematical statistics is a way to justify our analysis procedures. So you can see that even though our intuition would tell us, yeah, sample mean, xn bar, is the reasonable estimator population mean mu, but mathematical statistics can tell you more justifications about why it is reasonable. And it can tell you it's even the best, right? So it gives you those theoretical properties to say, yeah, it's unbiased, and among all the unbiased estimators, it achieves the minimum possible variance. So it's the best. Then if you should not consider other possible estimators to compete with it because it's already the best. So that's why you see math is useful. You are not just using empirical evidence to see, this one seems to perform best, but you have the theoretical justification. So you can save a lot of empirical efforts. I hope that makes sense. Okay, so that's the Cramér-Rao inequality. Okay, so now I'm going to introduce one last concept before we conclude today. So this concept is called relative efficiency. Okay, relative efficiency, short as RE, is to compare two unbiased estimators, theta 1 hat and theta 2 hat. So they both estimate the same theta. Okay, they are the same parameters, two estimators. So basically, we just define it. I think the definition is for two estimators, and it's defined as their variance ratio. So it's just the variance of theta 1 hat over the variance of theta 2 hat. So I don't think it's anything special. It's just that the larger the variance, the lower the efficiency. If you think about it that way, then it makes sense. Since both estimators are unbiased, then the only reasonable way to compare them is to look at their variances. Okay, so basically, if this RE, relative efficiency, theta 1, theta 2 hat, is greater than 1, based on this definition, if that's the case, then it just means variance of theta 1 hat is larger than the variance of theta 2 hat, right? And then we just say theta 2 hat is more efficient. Yeah, so I don't think this should be memorized. We should just add the variance bigger, efficiency lower, and that's good enough, right? The larger the variance, the smaller the efficiency. So efficiency is about how efficient this estimator tells you about the true parameter. Given they're both unbiased, their expectations are equal to theta. That's not a problem. But if the variance is big, then this estimator is more likely to take values very far away from theta, so it's not efficient. Okay, so I hope this intuition makes sense. All right, so finally, let me just give you this example before we conclude. So I'm going to leave you this, so you can do this after the class, just as a take-home exercise. And we'll get back to this next time. So let's say that we have n IID from a Poisson distribution. Okay, so let's say n is greater than 2. Okay, so we have two estimators. Lambda 1 hat is just xn bar, the average of everything. And the lambda 2 hat is just the average of the first two random variables, and it doesn't use the remaining random variables. Then the question is, are they both unbiased? That's the first question. Second question, which one is more efficient? Okay, I think your intuition should give you the answer immediately. And that kind of intuition is important for our data analysis, right? The intuition should be the one that uses more data should be better, right? And yeah, you are going to show this using the variance formula. So you are going to show that whether they are both unbiased, and the answer should be yes, and then what their variances are. Okay, so I'll stop here for today, and we will come back to our lectures next Monday. Okay, so see you. And there's a chat box question. Thank you. Okay.
Hi, Professor.
Yes.
I have a question. So how do we find the bias if the estimator is the minimum order statistic x1 or the maximum order statistic Sn? For example, this estimator, how can I find the bias?
Okay, we will talk about that actually in our maybe one lecture. We're going to talk about the distribution of those order statistics.
But this is, I think this is related to homework problem 4.
Okay, then maybe I will just send an announcement saying that we will defer that problem to later.
And this question also posed in our, let me see, in discussion form, but I didn't post that form. Our student post that question. So no, I hope you can.
Okay, yeah. So I think it's just so you will use the result. I will cover in the future lecture. We'll talk about the distribution later. So I will just postpone that question. Yeah.
Okay, thank you very much.
Okay, my pleasure.